Okay, so as I said, federated learning, now this is a very simple model, basically solver. But now, as I mentioned before, federated learning has a lot of issues. Now, I want to say here that issues mean research opportunities. So that's why federated learning is a hot topic in the research community, because there are different issues that need to be fixed in order to provide very stable and coherent federated learning systems to the end users. First of all, system heterogeneity. So what I mean by system heterogeneity, first, the fact that I just explained, non-IAD split of the data among the user, and this is basically the consequence. So in a kind of IAD setting, the local gradient of all the users will be very similar one to the other. And so when you take the average, you are somehow going towards the global minimum. Why? Because they can differ, but on average, the idea is that the direction of your gradient is towards the right kind of direction, right? And this is the global minimum. Non-IAD settings means that if you let one user to take a lot of local iteration, local epochs, that if non-IAD means that even the average of those gradients, or basically the global minimum, is different from user to user, but you want to find somehow a good aggregator of those global points, or local points, sorry. So here, if you let each user to go on and on with local epochs, basically they will end up having a very different solution in the end.
Sure.
And then if you keep the average of the solution, that does not work. It's like very bad performing model you have. So this is a very important concept of the learning, and this non-IAD setting is a very hot research topic for like analyzing all the convergence properties of the algorithm by considering non-IAD settings. Is a very it was solved for many problems, but is a very kind of important theoretical part of the research in federated learning. Other type of heterogeneity is like system heterogeneity. So here you can see each device may have a different computational capability. And so to perform 4 local epochs for one mobile phone can take 2 minutes, for another can take 10 minutes, because of course you may have different mobile phones and different computational capability. So here you can see basically you need to keep into account this. Another problem is network condition, like network heterogeneity. You may want to participate to this training round, but maybe your network condition is not the best one. I guess all of you experienced like bad network connectivities in some area of the world. So the idea is when that happens, you need to control that in your system design. Now, some solutions of these problems are present. For example, FedProx is a very well-known state-of-the-art baseline for non-IAD setting in federated learning. And here I just put this slide to give you basically a grasp of how it works. The idea is that locally, when a client minimizes the local function, they also have this regularization term.
Okay.
That you can see here. And this regularization term basically is keeping your new update, that is this W, close to WT, that was the initial model provided by the server.
Okay.
So the idea is to find the best model within some sort of ball, so within a ball of your initial model, in order that you don't have very far apart solutions locally here, so that when you can aggregate back these models, again, you have quite a good aggregation strategy.
Okay.
This is the idea behind this. They also have another parameter that control how many local basically updates you can do at the same time, but by considering the fact that the different devices may have different computational capabilities. But again, FedProx is one of the solutions. The literature you may read at the reference to see how you can tackle these two heterogeneity problems.
So basically here, Francesco, you are in this regularization term with the mu. Basically, you're penalizing a local model that diverge from too much from the one downloaded or provided by the network, basically. Okay. Yeah.
So find a good solution, but not go too far away from here, right? Because you want to stay within some mode of WT, basically. So yes, that is the idea. And of course, as you may think about, there are a lot of variants of these FedProx. There are many also new proposals. But again, this is one very good entry point, I would say, if one is interested in knowing more about this problem. And another way of tackling, for example, system heterogeneity was proposed for example, in this paper from iStats, but also in many other occasions, like asynchronous federated learning. So, but what I mean by asynchronous federated learning is that here we are assuming that at the end of each round, all these sample clients can indeed perform the model updates, and they can aggregate the model and send them back. Sometimes it may happen that one client is not able to provide updates within that time window. And so here the idea is that you can allow for the user to send back updates even at different point in time.
Okay.
And the idea is to have a buffer that collect all these updates before basically aggregate into a new model and send back the new model. Okay. So instead of closing one round in one specific time window, the idea is I may have one client send two models updates before one client send its model update.
Okay.
But still, once enough information has been collected, then they aggregate and they send back the updated model.
And I can imagine this aggregation might be done with a kind of weighted averaging. You take it probably. If you're more, I can imagine. The model that you provide is at time t minus 10. Of course, it would be less important than the one at t minus 3, for example.
Exactly.
Yeah.
So not this specific paper, but I saw some. So this is not kind of my expertise. This is asynchronous as well. But I saw something like that, where basically you weight the update considering basically the delay of those updates. So as you mentioned, that is one of the way you can tackle basically asynchronous federated learning. And this is basically the idea of buffering the updates and then aggregate and then send back the new models. But so also here there are many proposals, but the main point is being able to aggregate the models by not assuming that you have a strict time window for each user to send back the updates and then to receive again the new model, the new global model.
Okay.
Now, another problem is security and privacy. So the point is that security and privacy now is not 100% solved by federated learning, by vanilla federated learning. This is basically on the contrast with the centralized approach. This is designed such a way we can provide some security and privacy guarantees, but we're not 100% sure about it. So the point, as you can see here, even though data never leave the devices, the models update contain a lot of information regarding the local client's statistics. So this is a very interesting kind of piece of work. It was proposed in 2019 at InfoComm. There are others, similar papers that did similar things in slightly different scenarios. But the idea is that they're just samples of the victims. So basically, these are the local private data. When you send just not the data, but these model updates, if the attacker knows, for example, the global model and knows the architecture of the model, knows some information, and can basically catch, for example, by spoofing, by introducing it into the network, can catch these model updates, it is possible to reconstruct the data from these updates if there is no privacy mechanism working on that. So this is kind of impressive, but again, the statistics are there, right? Because you're sending, this problem can be mitigated, for example, just by increasing the batch size that you use to train your model on, or the local epochs, I guess. So you can, even the vanilla federated learning, if you use some strategies, you can make the life of the attackers hard. But still, you see that some statistics can be recovered even from just the updates and not just from the data. Now, some solutions the idea is to upload, instead of uploading pure models or pure model updates, is to inject some noise or to clip the gradient and send to the server this noisy version of the gradient. Peter Kairos is one of the most famous names in the privacy preserving learning algorithms and federated learning as well. And so this is one of the work. And also another work I put here, number 6, basically the idea is to analyze not just the privacy, but the accuracy privacy trade-off balancing this mechanism. So as you may guess, if I'm injecting noise into these updates, then it is harder for the server to synthesize the right global model and to converge to good solution. So you may lose something in terms of accuracy, right? Well, this is also a very interesting, I would say, because of my expertise, research topic. So how you can trade off the accuracy and privacy and also communication efficiency, as we see soon. So these are the idea behind privacy mechanisms. And now we're going to see the communication burden. So now I will put some more details on this because this is exactly my kind of expertise. So in the past few years, 2 years, I've been working on this topic. So again, as I said at the beginning, communication efficiency should be one of the benefits of federated learning. But nowadays, you know that ChatGPT is built on top of GPT-3. Now we have GPT-4. Who knows when GPT-5 will be online? So this model contains like tens of hundreds of billions of parameters. That means hundreds of gigabits of memory that you need to store this, but to run this model. So you need to store these programs, you need that much memory. And now federated learning, as I mentioned, we are not sending forth and back data, but the models themselves. So even the models now are huge, right? So we don't want to send all these, it's kind of a burden for the communication network.
Sure.
So even here, we have, of course, a lot of solutions, and the idea is lots of compression techniques emerge specifically for federated learning. They were studied and analyzed even in centralized setting. So the idea to reduce the size of a model has been there for a while, but then they're trying to optimize and to customize the solution for federated learning scenario. So the most kind of, I would say, the main 4 techniques to reduce the model updates and the communication burden and also the storage burden from these models are these ones, so like pruning or specification, quantization, low rank factorization, and random networks. I will go into some of the details of this in the future slides. Now, I also put a question here, is it better to compress the models or the data? Because now one can now think, oh, but maybe I can also do the same if you're not concerned about privacy, for example. I can send compressed version of the data. Even, well, if you can very well compress data, you can also reduce some privacy problems and send a compressed version of the data. So is it better to compress the data and train the model on this compressed version of the data, or send a compressed version of the the model of the real data and then send a compressed version of the model? So this is some question that with this paper that we will present actually in 1 week in Taipei at ISAT. This is just one part of that paper, but this is we provide some insights on this question in a very theoretical and simple and abstract model. But the idea is that it is better to send the model. I mean, theoretically, it should be the same. In practice, usually the models itself during the training is somehow a compressed version of your data set. But that compression has as target metric the final task that you want to accomplish. So somehow you are already compressing the data into your model in order to accomplish a good task in the right way. Whereas if you just send the data without knowing the task those models will be trained on, that is different. And so you need to further compress your data. So this is like a very theoretical question, but if you're interested, you can read the paper and reach out to me. Okay, so let me now briefly discuss the details of some of these techniques. So pruning, I want to say some words about this because these are a very milestone paper in the machine learning community in the past few years, and this is a very important paper, I would say. And this is not specifically for federated learning, so this was analyzed in a centralized setting. But then you can think of all pruning specification techniques that come out from this paper, they were used also in federated learning. So just to quickly go through this, the idea of this lottery ticket hypothesis. So what does it mean? Basically, researchers observed that you start from a network, and then you train this network on some task. In the end, basically, you can remove a lot of weights, let's say the less important weight, where importance can be L2, for example, like the magnitude of the weight. And then you start back at the beginning of the training with the same initialization that you had at the beginning and train this prune network. You go to the end, you further basically eliminate some of the parameters, basically the coefficients, and you basically start back again. If you do this like this for many iterations, you end up having a very well-reduced model. But impressive things is that you can see here from the picture that, for example, look at this, 1.2% of weight remaining, and you have basically the same accuracy, if not better, of the full model. That means 1% of the model in the end, but still have very good accuracy. Now, the point is, and the point of the paper is that if you start from this network, you won't basically obtain the same accuracy. So if you start from a very well-pruned network, you don't go to the same accuracy. The point here is that the training strategy itself, it seems that some redundancy is needed for the training process to find, that's why lottery ticket hypothesis, seems like there is a winning ticket within the huge model, the dense model, where the winning ticket is a subnetwork of this model that can perform well on your task. But you need, at the beginning, the whole model basically to find the subnetwork. And this is the idea behind the authoritative hypothesis. But the idea here that I want to convey to you is that huge models, probably they are very, very redundant in representing your function. So there are some ways of reducing all this redundancy to, to very well compressed model. So this is pruning, and this fact is exploited by some of the federated learning strategies. The second one is quantization. So this is more, as you may guess, very kind of standard old-style quantization techniques. Actually, in digital systems, everything is quantized. So even real numbers are represented by finite elements. So, but the idea is that instead of using, for example, 32 bits to represent each coefficient in the network, you may use, 4 or 8 bits to represent each of the components. Now, the idea is to perform here uniform quantization to have to decrease the precision that you use to represent the coefficients. But still, it seems that probably because of the redundancy I was talking about before, it seems that you don't need that specific, that very high precision to represent the updates of the model back to the server. So even by quantizing this model, you can still basically achieve similar, if not better, performance with respect to the 32-bit representations. Now, this is somehow stochastic way. Why stochastic? Because in order to choose which quantization level you want, you do it randomly with some specific optimized distribution. And this is to maintain, again, the unbiasedness of your grading computation. But these are details that you can find all these details in the paper that I point to you here. The key idea is that quantization still works a lot for federated learning. And you can reduce a lot the number of bits that you need to represent the weights in the network by using quantization. Now, the third method, this is the one I'm less familiar with, but is basically low-rank factorization. So as you may know from your linear algebra course, you can decompose a matrix, but a matrix is basically a linear transformation into two or more different matrices, depending on the task you want to accomplish. There are many ways of decomposing matrices. This is a way to find basically low-rank decomposition of your matrix. And what is this matrix? So this matrix is basically your layer within the network. So as you may know, within a network, one layer can be thought of like a matrix. So basically you have the output of the previous layer, that is the vector. You apply this linear transformation, and you have no linearities after this linear transformation that are the random transformation, sigma function, whatever you want. So if you look at this as like a linear transformation, you can find a similar representation. Of course, it's not like the same, but you can approximate this linear transformation by basically focusing on some of the dimension of this linear, basically a smaller subspace of your whole space of this linear matrix. So the point here is that you can find the same or similar computation by using less numbers in practice. So this was exploited by this power SGD algorithm, and these are, you can see here, the total training time to get more or less to the same accuracy for the uncompressed and the rank 4, 8, 16, and 32 is, way smaller in terms of hours. It can be even less than half of that. So again, this is a way to, because of course, when you can compress your network, then you can speed up convergence in terms of seconds, right? Maybe you need more rounds, but each round can last for a few seconds instead of many seconds if you have uncompressed version of your network. Again, I put the reference here. You can read the paper, all the references of this paper. There are a lot of work on that, even in centralized setting. It is actually optimized for distributed optimization. That means also for federated learning. This is actually, now we talk about random networks. And this is a paper basically I worked on, and we presented the paper this year in May at ICLR 23. So the idea of our paper, the paper is built on top of some of the insights provided by Ramanujan and colleagues in this paper, what's hidden in a randomly weighted neural network. This is a very fancy and interesting research topic, I would say. So the idea here, what you observe is that you start from a randomly initialized weight of a deep neural network. You can freeze the weights of the network and train basically a binary map to be applied element-wise to the weights. You optimize the mask to minimize the loss of data, and you can get impressive results. So what I mean by this is that you start from a random network, basically random weights, and you never touch those weights. You freeze the weights, and then on top of that, you train a binary mask that decides which way do I want to keep or remove from the network. in the end, you obtain an optimized mask, that is an optimized topology for your network, that you apply on top of these random weights, and you obtain basically a binary neural networks, because you can just reproduce your weights by a random seed, so it's like pseudo-random. But in the end, you are optimizing the topology of the network. And you can basically get very impressive results just by optimizing the topology of a random network. Again, here, the idea of the lottery ticket hypothesis, right? So we are finding a subnetwork works well, even though we are not training the weights of the network. We're just finding this network by optimizing the topology, and so which weight you want to keep and which one you want to remove. Now, this fact was exploited by me and Ivan Isik from Stanford University, and Saki Weissman as their supervisor, and Michele Zorzi and Dennis Gunduz. And we proposed this idea that is FedPM. And this algorithm is based on this insight. And the idea is that each client locally can start from, so here we exploited a stochastic way of training such mask, because now the point is, how can I optimize a binary mask? I cannot perform gradient descent on, binary values. So the idea here is that you start from trainable parameters that are real numbers, okay? You apply the sigmoid function on top of that, obtaining a trainable probability mask. So basically obtaining the same vector, but in the 0, 1, because the sigmoid take each value and maps into 0, 1 range. So these are the same dimensionality of the parameter vector of the network. And then you interpret this theta as a parameter of Bernoulli random variable. So you take a sample and you obtain this basically stochastic binary mask. So M of t can be either 0 or 1, okay? Then you apply this binary mask to your randomly initialized network that you never touch. Applying, basically element-wisely multiply the element, obtaining this randomly weighted sparse network, okay? So this is the way you can train, and then you backpropagate. So basically, you take this network, you see how it performs on some task, you backpropagate the gradient, not to this random weight that you never touch, but to this basically real parameter that is your score for your mask. So in the end, you end up having a well-optimized mask that can be applied on top of random networks and perform well. We exploited this fact in federated learning, and we further optimized this process in FedPM. So how it works FedPM, the idea is that locally, each client is performing that kind of stochastic optimization of the mask of the network. And then when you have to upload the models, instead of uploading the coefficient S or the parameter thetas that are still real numbers, you just take a sample of that mask by using the Bernoulli strategy, and then you communicate just this binary mask. So you can see here, each bit, so with different color, represent one coefficient of the network instead of having 32 bits. Okay, and so here each client can upload these binary masks to the server very efficiently. And then the server will aggregate by using a Bayesian aggregation strategy that we proposed to synthesize the new model. So again, here, for example, the aggregation is not just the average of the updates, but is some Bayesian aggregation strategy. So you can come up with many strategies that you want. And then you send back the real parameter now, and then locally you can go on training your models. So by using this method, we are able basically to outperform the performance of all, so basically to outperform all the state-of-the-art algorithms. You can see here we have QHGD that I explained before, SEN-HGD, that is a binary kind of variance of QHGD, third grad, and these other communication efficient federated learning strategies. So this work was proposed this year in this ICLR conference. And second row, you can see the bitrate actually that you need to communicate these samples. This is actually less than 1 bit per parameter. Why? Because we're using some, compression and coding techniques we are familiar with coming from telecommunication and information theory kind of background. So we can apply, for example, entropy coding to further reduce the number of bits that you use on average to represent one coefficient. And so these are very nice results, I would say. And actually, for you, Matteo, I have some new updates, and this is KLMS. So I won't go into the details of that because this is under revision for a conference, but this is again a kind of follow-up work that again I did in collaboration with Ivan Isik and these other professors. So here the idea is to further enhance all these standard methods. So we developed this module, this KLMS, that stands for KL minimization with side information. So as you may guess, it exploits KL divergence. And the idea is that this is not a standalone federated learning framework. but this is a module that you can apply on top of QHGD, on top of FedPM, SENSGD, Bayesian learning strategies. So there's also all the Bayesian counterpart of federated learning. This more recent kind of topic and less well basically investigated, but still a very exciting research. And so the idea is that KLMS is like a module you can think that can be applied together with all these state-of-the-art baselines. And this is a module that basically compress and code the updates in such a way we can further reduce the communication rate. If you look at this plot, this accuracy versus bitrate plot, you can see that the same algorithm, like QHD or FedPM, when we apply KLMS on top of these algorithms, you can further basically reduce the rate that you need to achieve the same accuracy. So basically, what we proposed just this year with FedPM, this same accuracy was achieved, just to give you an example, just by using 0.15 bits per parameter. So this kind of impressive results in terms of communication efficiency for federated learning. Hopefully, you will find these new results at the new conferences this year and also the code online. And I want also to mention that all these experiments were powered by Flower, where Flower is a very, very well-designed framework to perform federated learning and to scale mainly your federated learning experiments to many, many devices, even not just in a simulation environment, but also real-world devices. You can set a real implementation where you may have real hardware like Raspberry or other kind of pieces of hardware in the wild and communicate to those devices by using Flower. So this is kind of new updates on our work, and this also concludes somehow all this theoretical part of the talk. And I just want to now give you this slide where basically the research and the theoretical part and all the simulation parts are very important, but also the tools that you need to perform all the simulation, but also to bring federated learning to the real world. All these tools are very, very, very important. So I put here 4 of the main tables, if you want, tools or libraries that you can use to build and to scale your federated learning simulations. Again, I put Flower, is one that I'm more familiar with. Like I said, that Flower has a very exciting and vibrant community around that. They are based here in Cambridge. Is basically a project coming from the University of Cambridge. And now they are a well-established kind of organization, and with a very well, they have like monthly meetings and also yearly kind of summit. And you can see all the videos online with a lot of interesting research findings and implementations. FedML is like the US counterpart of Flower, if you want. So it was developed by a professor from University of Southern California with some of the PhD students, and is again a very well-established framework for machine learning. And or you can switch to the usual, big corporations kind of solution like TensorFlow Federated or IBM Federated Learning. There are other libraries out there you can use to basically implement your own federated learning strategies. But here I just put the one I'm most familiar with. Now, in the end, to conclude this presentation, I want to just give you some ideas and say some words about how you can contribute to this field as a master student, as a bachelor student, or as a new PhD student. If you want to dive into this topic and maybe you're wondering what else can we do in this domain. So theoretical research, of course, like non-IAD split optimization, convergence analysis in non-IAD scenarios with different kind of assumptions. This is always there are again still open problems. Bayesian federated learning, always we have open problems. There are some, of course, very nice and new results in the past few years, but still, I don't think we have it all now. The privacy communication accuracy trade-off. This is a very interesting and intriguing topic to me. So the idea is how you can increase privacy, kind of privacy guarantees, reducing the communication burden without affecting accuracy. As you may guess, this is a very tough problem because if you increase privacy, for example, you usually inject noise and reducing the accuracy. If I want to increase the communication efficiency, meaning reducing the number of bits I need to convey my updates, it can benefit the privacy because basically, for example, compressing, quantizing updates means having noisier version of your updates, but of course it will decrease again accuracy. So this is a very triangle that you can work on, and this is a very interesting topic coming from mainly from information theory kind of guys. And convergence analysis, also in a noisy environment like the wireless network. If you think of all these devices connected to the central authority wirelessly, that is many times the case. If you think of wearable devices, mobile phones, and sensors. Again, convergence analysis in these environments is still not easy. New vertical applications, so you can find new verticals. Like you can think of applying this distributed strategy in other, for example, in agri-tech, in whatever thing you may come up with. And also study when and how this federated learning strategy can be applied to the already established application. For example, healthcare, finance, autonomous vehicles. So how you can apply, or if you can optimize the pipeline for some specific application, that is still an open, kind of very interesting application-driven, if you want, research direction. And in the end, system and development. So, of course, the libraries that I showed you before still need to be enhanced, and the guys that are working harder and harder in order to provide very meaningful and well-coded and well-implemented tools to the researchers in order to make their lives easier. So it's not easy because, of course, as you may think, there are a lot of trade-offs that you need to optimize. For example, the more specific you are with a software tool, the less freedom you leave to the end user. And in this case, there are researchers on the other part of the pipeline. And the researchers usually need, for example, to reverse to do the opposite, or maybe to change the way things were done before. So not easy to see how you can provide a lot of flexibility to the researcher, but also to design some some meaningful to make some meaningful assumptions so that you can make the life of the researcher smoother and easier, right? And further design systems to implement these new findings in real world scenarios. Again, it is related to these software tools. Again, is an important direction I think that needs to be further explored. So with this slide, I'm just conclude my presentation. And just to wrap up some stuff, like with high probability, the majority of future AI systems will be distributed. So why? Because of privacy regulations, because of where the data are collected at the edge of the network by basically user devices, by sensors, and so on. It's a very hot topic for the learning, and there are potential gaps to be filled. So many intriguing research questions that like the one I showed you before. So if you're interested in the topic, feel free to reach out to me. And there are some very interesting references to start with. And if you want to, now the interesting thing is that here, being a system kind of level topic for machine learning, you can take basically some problems coming from other communities. For example, I'm coming from more telecommunication community. So that's why I'm interested in the communication efficiency of the problem, compression. And as you may see, then all these things then bound together in the end. But also privacy comes from information theoretic principles. But it's a very hot topic in machine learning nowadays. So if you come from control theory, you may have your spot. If you come from computer science, of course, from electrical engineering, you may design the systems so that they're very computational efficient, because then to be computational efficient, you need to integrate the software design with the hardware design. So there are a lot of very interesting topics here, and migrating from research to development is already happening. So regarding to your first kind of thought that you had, Matteo, from big tech to startups, they're already basically implementing federated learning on real world scenarios. If you think about your keyboard in your Android system and your Android mobile phones, the prediction of the keywords are made through federated learning. So those models are trained in this way. Now, feel free to reach out to me for further clarification. If you have an idea for collaboration on project or just for a chat, here is my email website, or you can find me on LinkedIn. And thank you very, very much for listening.
So, Francesco, thank you very much to you. I think I really appreciate this presentation, and we really, underline how much effort can be done in a presentation like this, where you try to combine higher level explanation of federated learning and really deep and cut-edge results. So I think I will really underline this to the audience. We have seen here some results that are actually probably available now on the whole federated learning community. So really, I think, really well done. I have one question, just one, on this point of application level, are you able to indicate, as far as you know, some application nowadays that are really use federated learning? Maybe in our smartwatches or smartphone. I mean, are you
Yeah.
aware of some application that is really using those at the moment? Because I come from sensor fusion, so I'm really interested in this kind of stuff. I can tell you that as far as I know, in the community of sensor fusion, so it's not something that is really used at the moment in the companies. But I say at the moment. But I'm pretty sure that there will be maybe some some services that are really hold on that. So, what is your point here?
Yeah. So that's a very excellent question. The point is that for sure, I'm not 100% sure about which application I is using. For sure, the keyboard, kind of a framework is using this federated learning system design. The point is that specifically which kind of application, I don't know, but I know that. So, for example, as you may know, I was at this flower event like 1 month ago here in Cambridge, and I can say for sure that there are banks and there are for example, browsers like Brave. That's a very interesting startup project coming from the San Francisco startup Brave. And they have now a research center in London. And basically, they are collaborating actually quite, heavily with Flower and with this open library to create the substrate for having the federated learning into their products.
Okay.
So maybe nowadays, I don't know exactly who is using this, but I can say with quite high confidence, basically probability in the near future, you will have many more applications using, because the point is that this infrastructure, like also from the programming point of view, that they're not already there, but they are developing now the libraries. But another important, if you want, there is another company that is using this for health application. I don't remember the name, but there are some results also from the Stanford guys. They collaborated with some of the hospitals in the US. And basically, they were able to improve the performance of a centralized model by collecting data from many hospitals in terms of, for example, MRIs, I think it was, by using federated learning.
Okay.
So it was not like a end user product, but still a very well done, I would say, research project.
Well, I think this is a perfect situation. This is a really fantastic message for all the investors. I think we have really well, I would say, quite well understood research, but which is not applied at the moment. So that means a lot of possibility in terms of putting in the real world the frameworks and the tools that Francesco has explained. So I think we have covered now the picture of federated learning. So I will thank you again, Francesco, for accepting this lecture. And again,
you for having.
Yeah, if you want more from Francesco, he has put his own details and contacts here. So thank you very much, and hope to see maybe next year for an update on federated learning 2024.
That would be great. Thank you, Matteo, again.
Bye.
Bye-bye.